Alright guys, so on this video I'm going to talk about the algebra of functions. But before we get into the algebra of functions, I'm going to give you a brief introduction into how to find the domain of a function. We already talked about this on previous sections in 2.2. So when you have a graph, you have a Cartesian coordinate and you have a graph, to find the domain of this function, it means to find how many x values are available for this graph, right? In this case, since this line extends all the way to infinity, but then the domain is going to be positive infinity, and on the left side, or the smallest number available for this line, is going to be negative infinity, because this line extends all the way to the right and extends all the way to the left, right? So my domain on this line will be from negative infinity to positive infinity. That will be my domain. But what if I give you an equation? Can you find out the domain of this graph without doing the graphing, of course, but by just looking at the equation, can you find what is the highest and what is the lowest value for this graph, right, for the domain? So, for example, if I give you an equation that looks like 2x plus 3, I'm just going to call this a function. What would be the domain of this? If we transform this into a graph, what would be the highest value and the lowest value of the domain on this graph, right? So if you go to a graphing calculator, which I have somewhere around here, I'm just going to put the value for this equation, which is 2x minus 3, and then I'm going to have the plot of the graph. And if I zoom out, you're going to see that this line just keeps extending all the way to the infinity, right? Or then I'm in my, my 200s. If you see the first value of this coordinate, that's 56, that's 119. So all of those numbers are part of the domain. That's 200, the little value in the coordinate, right? And if it keeps going, this is just going to keep extending. So the domain on this line is going to be, or the highest number is going to be infinity, right? And if you go to the left, or to the negative domains, right? That's negative 110, that's negative 141, that's negative 200, and so on and so forth. So can you see that the domain of this line is going to be positive infinity and negative infinity? Okay, so what we can say is that for any equation, the domain is going to be all the real numbers. Or in other words, negative infinity to positive infinity for every single equation. Now, for like every other situation in life, we have exceptions to this rule, right? So the domain is always going to be all the real numbers, but we have to include two exceptions, right? All the real numbers except denominators that cause division by 0. So those numbers are not going to be part of the domain, and I'm going to show you why. And the other situation is numbers that cause I'm just going to I'm not going to use the letter A, I'm just going to do letter N, whichever letter, right? So numbers that cause a negative square root. So if I substitute a number into a square root, and this gives me a negative radicand, the radicand is the number inside the root, then that number has to be excluded from the domain. Okay, and let me show you just two quick examples of situations where the domain is not all the real numbers. All of the equations, the domain is all the real numbers, but there's some situations or exceptions where the domain is not going to be all the real numbers. This is where I'm going to take one from the PowerPoint that says f of x equals 1 over x minus 5. So at this point, can you see I have a denominator, I have a variable in the denominator, right? So it means that my domain is not going to be all of the real numbers, because if I have a variable in the denominator, there is going to be a number that if I substitute into that equation is going to give me a 0 in the denominator, right? And if I have something like this, 1 over 0, then this does not have a result. That means that whatever causes a division by 0 is not part of the domain, so we have to exclude this number. So how do I find which is the number that's not that's going to cause a division by 0? Well, you take the denominator, the whole denominator of this fraction, x minus 5, and I'm going to set it equal to 0. Not because I want it to be 0, but because I want to find what is the value that if I substitute in here is going to cause my denominator to be 0. And if you solve this very simple equation, I'm going to add 5 to both sides. So x equals 5. This is the number that is not part of the domain. So my domain for this graph or for this line is going to be all the real numbers except positive 5. Because can you see that if you try to find, I'm going to try to find f of 5, right? I'm going to try to substitute 5 in here. You're going to get a division by 0, which has no result. That means that 5, the number that I substitute in here, is not part of the domain. It means that 5 does not have a correspondence in the graph. So let's take a look at this line, right? I'm just going to plot this equation into Desmos, the graphing calculator that I'm showing you right now. Okay. So this is my previous equation. I'm just going to delete this. My new equation is going to be 1 over x minus 5. So this is what my equation looks like. I'm going to zoom in a little bit into the smallest numbers. Okay. This is what this function or this function looks like, right? So at this point, this does not have a correspondence in 5, right? When the value is 5, that 5, domain 5 does not have a correspondence in the graph. It looks like those two curves try to touch the number 5, try to have a correspondence in the 5, but they don't really have a correspondence in the 5, right? So if you take a look at the domain, over there my domain is 0, right? If I keep going to the right, that's my domain is 1 over there. My domain is 2, my domain is 3, my domain is 4. So all of those numbers are part of the domain, right? And if I keep going over here, the number is going to get close and close and close and close and close to 5, but it will never reach 5. So this kind of graphs that approach one point, but they don't reach that point, we call those asymptotes, right? So this is an asymptote graph. As 4.9, I'm going to zoom out just so you guys can see. It looks like it approaches 5, but if I select any of those points, as 4.97, it's never going to touch 5. If I go further down here, that's 4.99 over here, right? It's never going to touch 5. So this graph at 5, it does not have a correspondence. So we have to exclude the number 5. But again, we don't have to do any of this because just by looking at the equation, we know that the number that doesn't have a correspondence in the graph is x equals 5. This is the number because we take the denominator, we set it equal to 0, right? X minus 5 equals 0. We solve for that equation. So the result is x equals 5. I know whatever this graph looks like. If this is my domain 5, there's going to be an imaginary line in here that those two graphs are never going to meet, right? Those two graphs are never going to meet. So this is one of the situations, and this is the only situation that we're going to encounter right now. When you have division of variables, when you have a denominator that has an x, then the domain is not all the real numbers. The domain is all the real numbers except x equals 5, or except 5, right? So if there's a way that we can represent this, we know that all of the numbers, all the way from negative infinity to 5, not including 5, are part of the domain. And also, all the numbers from 5 all the way to positive infinity. So that is my domain. Every single number except 5, we have parentheses in here to denote that 5 is not part of the graph. If you substitute 5 in the function, what happens? You get a division by 0. You get a division by 0, it means it does not have a correspondence in the graph. I'm going to upload another video, and this is going to show you some other examples of how to find which numbers to exclude from the domain.